Welcome to Data Science with EJD. We're still talking about the clustering under unsupervised learning, under machine learning. So in the previous video, we had talked about Gaussian mixed models for clustering. Now we are taking something advanced as far as clustering is concerned. Um, Okay, I don't know. I think I mentioned in the last video that that was the last. No, this should be the last under clustering. And after this one, we'll be going ahead to talk about dimensionality reduction, which is also one of the set of algorithms you can have in under unsupervised learning, which deals with unlabeled data. That is, you have the input, whatever input data you have is just going to be categorized into patterns, or you're going to see it's going to be categorized into clusters, so you're going to see patterns in them and everything. Unlike supervised learning, where you have your inputs called features, and those inputs are actually used to measure a particular target, which is your output, right? So spectral clustering is what we are saying here, and it is some advanced form of clustering. So by way of introduction, okay, I think I want to. Should I call this into bits? Doesn't make any difference. Okay. Spectral clustering is a class of algorithms for grouping data points into clusters based on the eigenstructure of a similarity graph derived from the data. I have a whole playlist on graph theory, graph and network theory. You want to check that out under the playlists. So that can give you an idea of what a similarity graph looks like. Unlike traditional clustering methods such as k-means, which operate now, you discover that every other clustering we consider, we always have to refer to k-means. K-means is some kind of baseline kind of clustering, like the most basic form of clustering you can have. All right. So, unlike traditional clustering methods such as k-means, which operate directly on the original feature space and rely on assumptions of convex spherical clusters, spectral clustering leverages graph theory to uncover complex cluster structures. So we have some bit of complexity. I mean, some sophistication, if you like, as far as spectral clustering is concerned. Now, when do you go for spectral clustering? One of the reasons you go for spectral clustering is when data lies on a manifold or contains clusters within non-convex shapes, right? Then Euclidean distance poorly represents similarity, or you want to cluster data using pairwise similarities rather than explicit coordinates. Then the dataset is moderate in size due to eigenvalue computations, right? So core components of spectral clustering. Spectral clustering hinges on two major components. You have, first of all, the similarity, and then you have the graph Laplacian. I think we talked about all of this on the graph and network theory. So similarity or affinity matrix S. This represents pairwise similarities between data points, and it is a symmetric n by n matrix. It's a square matrix, that is, where n is number of points. Then entries Sij quantify how close or related points I and j are, and choice of similarity affects clustering outcome dramatically. Now we have common ways to build S. So we have the fully connected RBF kernel. I think RBF is reader basis function. I think, yeah, fully connected RBF kernel. Sij is the exponent minus absolute value. Is that absolute value or even norm of xi minus xj squared, and then you have 2 sigma squared. So where sigma controls the scale of neighborhoods. Then we have k nearest neighbor graph, k nearest neighbors, knn graph. So you connect points I only to its k nearest neighbors with weights often computed via RBF kernel or set to 1. Then we have the epsilon neighborhood graph. So this connect points if distance is less than epsilon. I think we saw the idea of epsilon when we talked about must have been under DB scan, density based spatial clustering for applications and noise. I think then we have so another feature, another core component of spectral clustering, apart from similarity or affinity matrix, is the graph Laplacian. So the graph Laplacian is a matrix that encodes the connectivity and structure of the graph defined by S. Okay, I think I should write this better. Um, I think using dollar signs we get the FS sharper. This would have worked in other environment, but it's obviously not working in Jupyter Notebook. But this is fine. Still, we can make do with this. So the graph Laplacian is a matrix that encodes the connectivity and structure of the graph defined by S. So degree matrix D is diagonal. So we have DI summation over all the J's of all of the SI's. So it's more like you have SI1 plus SI2 plus SI3 down to the last. Then we have unnormalized Laplacian where we have L equals D minus S. Then we have the normalized Laplacians, that's symmetric normalized. So you have L sim D inverse, LD inverse equals 1 minus D inverse, SD inverse, like that. Then you have the random walk normalized. So that's L sub RW. So D inverse L equals I minus D inverse S. Then for the properties, you have L is symmetric and positive semi-definite. If you don't know what this means, you can check my very first playlist on this channel is on matrices. So I talked about definiteness, whether it's something is semi-definite or positive definite or negative definite, things like that. Eigenvalues of L of course, L is the graph Laplacian, right? Eigenvalues of L Laplacian provide information on graph connectivity. The number of zero eigenvalues equals the number of connected components. Eigenvectors corresponding to the smallest eigenvalues carry cluster membership information. So, this is also using some of these ideas. I mean, I think under numerical analysis, I got to a point where I did some things strictly on eigenvalues and eigenvectors. So they can give a whole lot of information depending on the context we are working in. So the spectral clustering algorithm step by step. Now, step one, construct similarity matrix S and decide similarity measure and graph construction, right? Um, okay, I think this should be, where is that now? Step one. Okay. Like I need to, like it needs to be on its own a bit. So construct similarity matrix. Okay, let me just use it like that way. So step one again, construct similarity matrix S, and there you're deciding similarity measure and graph construction. E.g., you want to use radial basis function kernel with parameter sigma. Step two, you compute degree matrix D. Diagonal entries are sums of rows of S. I think I did something like this on that graph theory at some point. I had a very big graph like that, and I was trying to do the subtraction. It could really get messy if you're doing it manually, like I did in that place. In step three, you compute graph Laplacian L. So you choose unnormalized or normalized version depending on data characteristics. Normalized Laplacians are often preferred for better numerical stability and performance. Then step four, you compute the first k eigenvectors of L. So you compute eigenvectors corresponding to the k smallest eigenvalues. This n by k matrix U encodes a low dimensional representation preserving cluster structure. Step 5, row normalize U if using normalized Laplacian. Each row is scaled to have unit norm. Step 6, you cluster rows of U with k-means. So apply k-means to U rows to assign data points to clusters. In step 7, you return cluster assignments. So let's talk about mathematical intuition behind spectral clustering. Data points are viewed as nodes of a weighted graph. All right. So we view each data point as a node of a weighted graph. Then clusters corresponding to subsets of nodes that are densely connected internally but sparsely connected externally. Then minimizing graph cut metrics like ratio cut or normalized cut is equivalent to solving an eigenvalue problem involving L. Then spectral embedding transforms data into a space where clusters become linearly separable. No, these are basically graph network theory stuff. We're talking about graph theory things all the way. So if you want more light on graph theory, I have a whole playlist on graph theory that you can check out on the channel. So when to use spectral clustering versus k-means, right? Number one, based on what assumption? So, if clusters are convex and spherical, you use k-means. If cluster has no shape assumption, and handles complex shapes, then you use spectral clustering. The input now, you have feature vectors, you use k-means. If you have pairwise similarity matrix, you use spectral clustering. For computational cost, for k-means, of course, it's low because it scales well to large data sets. But computational cost for spectral clustering is higher due to eigen decomposition, because you have to deal with eigenvalues and all of that, so it's a lot of work there. Then for the cluster shape, k-means works poorly on complex shapes, while spectral clustering is excellent for non-convex clusters. Sensitivity, k-means is sensitive to initializing and outliers, while spectral clustering is more robust with well-constructed similarity matrix. Criterion example use case, K-means is good for well-separated blobs. All those data points that are gathered that you can easily see them in clear clusters. For spectral clustering, it is good. You can use it for two moons or concentric circles or social network communities. So if you're working on social network, you definitely know you want to go spectral clustering. Okay. So let's look at the implementation. Let's see how that can be implemented in Python, right? Um, so want to look at Python implementation for spectral clustering versus k-means on two moons data set. So two moons data set is a canonical example where k-means fails due to non-convex shapes, but spectral clustering succeeds. So if you have non-convex shapes, k-means is bound to fail, while spectral clustering is good to go. And because you're using k-means, you see line 1 to 5 again, it's just to suppress an error that might come. So, in fact, maybe in this case, I'll remove it when I get to that point so you can see the error and how this suppresses that. So, of course, we need NumPy, Matplotlib, and we need from the data set. Now we need to make the moon's data set, and then for the cluster, we need both k-means and spectral clustering because we want to compare them. Then the metrics, we need adjusted rand score. Of course, for clustering, we see that the adjusted rand index is what helps us to see. The closer to one, the ARI, that's the adjusted rand index is, the better the result. So next, since we're talking about the moons, right? We want to generate synthetic data sets. So we have X, Y underscore true. So make moons with 300 samples and 0.05 noise, random state 42 for reproducibility. So visualize ground truth clusters. So you plot the cluster. So for the ground truth, now those are the original two moon data sets. So whatever you have here is what you're going to see here directly. Nothing has been done to that. Okay, so and since it is 2 months, we are going to see like 2 moons, trying to shake in a kind of handshake, so to speak. Step two, apply k-means clustering. So k-means is equal to k-means. So you are training the data on k-means model here. That's what is happening in line 22. K-means is k-means n clusters equals to random state is 42. So y underscore k-means is now k-means fit predict. This is why you are getting the value for k-means here. And you can now plot that on a scatter plot, just like you did for now. This is your raw data. This is now you using it on k-means. Then you can now print k-means adjusted rand index. So you get the index right here. Then you can now apply spectral clustering with radial basis function kernel affinity. So you go spectral now. You have spectral clustering, n clusters, you have two. Affinity is radial base function, gamma is 15. That is kernel with tune as needed. So you can always change this gamma as you like. We saw that gamma before. That's gamma underscore ik. Then the assumed label, you have k means the random state is 42 for reproducibility. And then this is where you now train the data. You train the model with the given data train the spectral clustering model with the data you have. That same X you have up there. And then we also plot that and we see the spectral with adjusted random index to see which works better. So I run this now. So you see, we have this result. But before I even talk about that, I promised I was going to show you why we need these first 5 lines, right? So if I run it this way now, you're going to see an error generated after it's all done. Oh, I think it's working fine here. Okay, you know what? I'm going to run it from the beginning so I can emphasize what I want to show you. So I have this. I restart and run all cells. Yeah. So, I mean, when you write a whole code sheet, by the time it's all done, it's better you run it from the beginning like that to see, yeah, to see if there's any problem. So you can see some errors here. K-means is known to have a memory leak on Windows with MKL where there are less chunks than available threads. So you can avoid it by setting the environment variable OMP num threads equals to. So that's exactly what these 5 lines are for. So we say OS environment OM num threads equals to, and we actually import warnings and we are filtering the warnings. We don't want the warning to show. That's why we put that. So you see, once I put that now, the warnings are gone. So now to the results. This is what the original 2 months data set looks like. Of course, it's made up data, right? So we have, this into this like that. That's the original. But when you train the data on k-means when you train the k-means clustering model on the data, see what it gives. You have something that is not quite the original thing. So based on its own thinking, see what it gives. So you have an overlapping region like this, so to speak. And then the k-means adjusted ARI, the k-means adjusted round index is 0.25. That's pretty low. That's really, really very low. But when you do it with spectral cluster, which we did the other time, so the spectral clustering adjusted rand index is perfect, 1.0. So it gives you what exactly what you have up there. Except that the color is inverted, but at least you have the data points clearly separated exactly the way they are here. So you see this is a 0.5. So despite that the fact that the color is even changed, it's still good to go. So this is perfect for spectral clustering, but k-means fails in this situation when you deal with 2 months data set. Okay, explanation of code and parameters. So make moons create two interleaving half circles. Yeah, okay, the word is interleaving. Half circles with noise. And K means clusters based on Euclidean distance, which fails to separate moons well. So you couldn't separate the moons well because you have some overlapping edges. Then spectral clustering uses affinity RBF. So it constructs similarity matrix using Gaussian kernel. The gamma is 15, which is inverse kernel with higher values make affinity more local. Assigning labels, so you can play with that 15 for sure and see what happens. So assigning labels, k-means uses k-means on spectral embeddings. Then it uses k-means on spectral embeddings, right? Adjusted rand score compares predicted labels to true labels. One means perfect clustering, just like we have for spectral here. So I just want to play with that number 15. Where is that now? The gamma value. Where is that now? Okay, yeah. So I want to make it like can I make it 50 and see what happens? So this is how we learn. Let's see. Uh okay, I mean we're only going to identify it here. Okay. Uh yeah, nothing serious. Maybe it just makes it bolder or something like that. Okay. So let me take it back to 15. 15. Or let me make it 150 and even see what it's gonna look like. Yeah, it's done. Okay, nothing serious. Or nothing really serious. Okay, nice. So let's leave it at 15 then. Okay, so now that this is done, let's talk about some practical considerations. So choosing sigma or gamma in similarity matrix. So this controls neighborhood size in similarity graph. Too small will give you the graph becomes disconnected. Too large graph becomes fully connected, losing structure. Then scaling to large data sets. Eigen decomposition um, of n by n matrix is expensive. Approaches include approximation, sparse similarity graphs, or landmark-based spectral clustering. So if you followed the playlist, or if you check the playlist on eigenvalues and eigenvectors, you can see the process can be really tedious, even for a matrix as simple as 3 by 3. So it's not as easy. So the robustness spectral clustering relies heavily on similarity matrix quality, and the preprocessing you need feature scaling and parameter tuning to be essential. Those are essential. So, looking at the steps now, we're talking about summary. So, look at the steps. Construct similarity graph S, and that is pairwise similarity with kernels or neighborhoods. Compute degree matrix D, diagonal sum of S. Compute graph Laplacian L. Laplacian L equals D minus S, or normalized variance. Eigen decomposition, extract k smallest eigenvectors, embedded data points, form matrix U with eigenvectors, normalize rows, which is optional for normalized Laplacians, cluster in spectral space, run k-means on rows of U, assign original point based on k-means label. So that's a lot of work going in the background. But thankfully, the model is suited for that. So you see that spectral clustering is a powerful method, bridging clustering with graph theory. So if you need graph theory applied in clustering, spectral clustering it is. So particularly useful for data with complex nonlinear structures where classical clustering methods fail. So with this, we are gone through. We are done with clustering under unsupervised learning. From this next video, I'll be talking about dimensionality reduction, talking about things like PCA, TSNE, and all that. Right. So let me know how helpful this video is for you. Let me know if there's something you'd like me to try out. If you have subscribed already, thank you for that. If you have not, please go ahead and subscribe and be sure to like and share so that more people can have access to this great content. Don't forget to hit the notification bell so you can always get alerted each time a new video is released. on my channel, you can now become a member. Just click on join. You see different levels of membership and the possible benefits you stand to gain by being a member of the channel. Right. Till I come your way again, keep doing data right. Bye.